All right, welcome to the hard part of Unit 6. It's called EMF, free energy, and the equilibrium constant. Let's get started. So, since both Gibbs free energy and cell potential represent the thermodynamic favorability, again spontaneity, of a process, we can, coincidentally relate them with that following equation. Delta G equals negative NFE. And I'll explain what N is in just a bit, and F. So delta G equals negative NFE. In this case, N refers to the number of moles of electrons transferred during a redox reaction, so that coefficient of electrons. And F is what we call Faraday's constant. Well, a guy named Michael Faraday invented it. That's why it's called, discovered it. That's why it's called Faraday's constant. But again, N refers to the number of moles of electrons. And Faraday's constant, named after Michael Faraday, tells us the charge of 1 mole of electrons. So he says that the charge of 1 mole of electrons is 96,485 coulombs per mole, which then we can also think of as joules per volts times mole. And, yep, everything's going to end up kind of being related. So when they're in their standard state, that above equation becomes as follows. The number of moles won't change, the Faraday's won't change, but we do have our standard cell potential. And through substitution and some reconfiguration of previous equations and a little dose of really just mean chemistry, you get kind of a wonderful equation. It gets a little better. That our standard cell potential is equal to RT/F natural log of K, which means we're relating gases, temperature, which kind of refers to kinetics at times, our moles of electrons, Faraday's constants, and our equilibrium equation. Now, Gibbs is not quite directly in there, but we got this relationship by actually substituting in a previous equation for our delta G. However, it gets a tiny bit crazier. All right, so welcome to the beginning of hard problems. I'm actually going to walk you through part of this and let you go through the other. It's just there's a lot of stuff that really takes seeing it a few steps ahead before you can actually do. So we're looking for a standard free energy change, and the only equation we have that really can help us with that is that delta G equals negative NFE standard. So the only way to get that is we mainly need to find our standard E, which means we need to find our cathode minus anode, which means we need to find oxidation and reduction. So first we got to figure out what oxidizes, make our oxidation reduction reactions, and then we'll also be able to see what our N is. F's always a constant. We'll calculate our E using the chart with all our SRPs, and then be able to find our delta G. So I'm going to say pause, find the reactions, balance them, get their SRP values, and see if you can find our standard E. Come back in a bit once you've tried that. All right, welcome back. Here are the two balanced half reactions we have. I basically just split apart the top equation. Okay, if you haven't found the cell potentials, find them now. If not, here they are. So this one is positive 0.799, positive 1.23. Okay, we have cathode minus anode. Cathode is our reduction, anode is oxidation. That means that our cell potential is going to equal positive 1.23 minus positive 0.799, which is equal to a positive 0.431 volts. We can now plug that into the top equation up here and get our delta G. So I'm going to say pause a bit, try and figure that out, come back in just a bit. Okay? When you plug that in, you'll see that we are transferring 4 electrons. So that's a 4. Faraday's constant, our cell potential, gets you about negative 166 kilojoules. That is our standard delta G for this reaction. And keep in mind, we didn't use any delta G values. We didn't have a chart of thermo. We just based this off the likelihood that these things are to reduce. I just find that kind of cool. Most of the stuff that we thought we had to have for delta G, turns out you don't. All right, now let's work on the second part, give you a bit to write this down, and then we're going to start working on the equilibrium constant. All right. Well, this is basically my hint. You're using that equation. Good luck. Take a few minutes, work on this, come on back. All right, so here is basically the work. Cell potential, R, temperature, amount of moles transferred, Faraday's. Take all this, multiply it together, divide this by that whole thing, you get this. To cancel out the natural log, you raise you raise both powers. Do that. E to the 6, 7.4 is that. Crazy, stinking, huge equilibrium constant. But our Gibbs is almost negative 200 kilojoules. This is insanely spontaneous, which means, of course, we're going to be heavily product favored. That, however, is your final answer. Oh my goodness, that was intense. But there you go. All right, last kind of death equation. The Nernst equation is a wonderful equation. It allows us to do all that stuff, however, at not standard conditions. So, E standard minus this fluff factor again, and we're using Q, very similar to last time in our unit 5. And again, we're relating almost everything again at any conditions we have. So, it also explains, however, why the EMF of a cell drops as the cell discharges, meaning it actually can explain why batteries die. So let's go to that. As reactants are converted to products, as we use our battery, the value of Q increases, okay, because we slowly get more products than reactants. If our Q increases, then our value overall of our non-standard E will decrease because it's subtracting a bigger number from the standard. And eventually you'll get to the point where your E will actually get down to 0. Okay? A while ago we realized that if our E is 0, going back to the equation of delta G equals negative NFE, if that's 0, that means our delta G is 0. Which means that once it hits 0, we're at equilibrium. Nothing's going to change. It's going to stay there. Batteries aren't going to have any kind of power to them. So again, reactants going to product increases our Q. By increasing our Q, let me give you that equation again. Sorry. By increasing Q, this is going to be a bigger number, which means overall will be a less positive number. Okay, eventually though, you're going to subtract enough where you're actually going to get this to 0. You're going to basically decrease it enough, or at least get closer and closer to 0. And as you get closer to 0, you eventually will hit equilibrium. And again, nothing occurs. So there you go. Increase in the concentration of our reactants, or decrease in even the concentration of our products, ultimately will increase our force, because that means Q will actually decrease. You kind of shift it back a bit. And obviously the opposite will cause Q to increase and decrease the EMF. But that's how we recharge batteries. We kind of reverse our reaction, and thus it can kind of restart again until it eventually hits equilibrium again. So, there you go. All right. So we need to calculate the EMF at 298 Kelvin generated by a voltaic cell in which the overall reaction is this. Sorry, I couldn't quite fit on one line. However, it's not at equilibrium. So we're saying, basically, what's our overall force? If that's our concentrations, good luck. All right. So now that you've worked it a bit, let's kind of, obviously work through this. We are using the Nernst equation, which is that RE, so what we're looking for equals our E standard, minus RT over in F natural log Q. So, a couple things you probably figured out. We need to find our E standard. We need to find our Q. All right, So if you were to actually calculate this out, find the different oxidation equation and the reduction equation, both of which I'm sure you can do, you will find that our E cell, then you find your cathode and your anode, do your cathode minus your anode. Your E cell will be 0.79 volts. So I'm not writing it, just really am low on room on this. Our Q, though, let me show you that. So our Q will equal, let's see, Cr3 plus squared over Cr2O7 H plus to the 14th, oh my goodness, times I minus to the 6th. All right, you plug in those values because they give you dichromate, they give you hydrogen, they give you iodide, and they give you chromium. Plug those in, you get somewhere around 5.0 times 10 to the negative 11th. With that, we have our E standard. Our R is always the same. We're at 298 Kelvin. In your oxidation, it ends up being transferring 6 electrons. Again, I'm going to let you do those reactions. You know how to do them. It's just bouncing half reactions. And F is always a constant. We just found our Q. Plug things in, and you will finally get our answer. With that, we end up getting about 0.89 volts. Now, I know I skipped almost all the work. I also know that you can totally do it. You are literally just plugging in the values for this. The one thing that you'll need to know is that our N will equal 6. And that's because if you were to find the oxidation and reduction reaction between these, you'll end up having 6 electrons being given in the oxidation, 6 electrons reacting in the reduction. With that, though, that's how you use the Nernst equation. Kind of long, crazy looking equation, but really quite doable. So yeah, thanks for watching.